This video will describe how to tune the motors on your L-Series mount for optimal tracking and stability. After installing your L-mount, you may find that it initially behaves in a surprising way. For example, it might make a loud noise and track poorly when you first enable the motors, like this. Or you may find that the motors are quiet when you enable them, but it barely resists you when you try to push the telescope out of position, and it takes a long time to zero back in on its target, like this. You may also see your mount behave like this if you make a significant change to the payload of your mount. For example, if you remove a small telescope and install a larger telescope. In any of these cases, we need to retune the motor parameters to match the payload of the mount. Motor tuning is a concept that is unfamiliar to most first-time users of direct drive mounts, but with the PlaneWave AutoTuner tool, you should find it straightforward to get up and running with a well-tuned system. Once the system is properly tuned, you should find that the telescope is nearly silent at all times when the motors are enabled, and the mount should resist your attempts to push it out of position, and it should snap back to nearly zero error very quickly. To begin tuning your mount, first make sure that you're running PlaneWave Interface version 4.08 or later. You can download the latest version of PlaneWave Interface 4 from our website, planewave.com. Make sure that you are connected to the mount, and then go to the Commands menu and locate the option to run the AutoTuner tool. This screen explains that you're about to disconnect PlaneWave Interface from the mount and run AutoTuner, which will have its own connection to the mount. Once AutoTuner launches, select Connect to Mount, and then choose the Measure Payload option. This screen explains what's about to happen. First, the mount will oscillate back and forth at low frequencies, and then medium frequencies, and eventually it'll be going back and forth at such high frequencies that you'll hear sounds coming from the mount. This is perfectly normal, and this process is to fully characterize the mechanical system of your mount. On the next screen, select the type of mount that you have. In this case, I'm tuning a system that has an alt-az geometry. On the next screen, we can describe the payload that we're tuning. In this case, I have a CDK14 with an eyepiece. And down here under Notes, I might just say that I recently rebalanced the system. When you run the tuning process, it's extremely important that you have a well-balanced system. With the motors turned off, you should be able to manually move the mount to any position, let go, and the mount should not significantly move from that position. By filling out this form, you come up with a project name down here, and this project name just describes what kind of system you're tuning. This can be useful if you ever need to send this data back to PlaneWave for analysis, and it can also be useful if you need to swap between different configurations. For example, if you swap between a 1 telescope configuration and a 2 telescope configuration, or even if you go from a very heavy camera to a very lightweight eyepiece. You can also edit the project name as needed down here. On the next screen, you select the type of scans that you want to do. For a brand new installation, you almost always want to scan both axes, but if you're coming back just to refine the tuning on a single axis, you can select to tune just the azimuth motor or just the altitude motor and save a little bit of time. Over here, you select the scan density, which is just the number of positions where you perform what's called a frequency sweep. If you just want to get the system up and running, you can do a quick scan, which will do 2 scans at the same position, one for altitude and one for azimuth. A normal scan is probably the best thing to get started with. This, as you can see, will do 4 scans, 1 position in altitude and 3 positions in azimuth. And if you have a lot of time on your hands, you can do a thorough scan, which will do many scans at many different positions. The 3D representation over here allows you to preview where it will be performing these scans. And if you click this checkbox, you can click on one of these lines and see where the mount will be pointing when it does each of these scans. For a large system like an L600 with a CDK24, it can be very beneficial to do a thorough scan, especially if it's in an equatorial mount. If you have a smaller system like an L350 with a 14-inch or an L500 with a 17-inch, you should find that a normal scan does just fine. Today I'll do a quick scan just to illustrate the process. After clicking Next, the tuning process begins. First, the mount will find its home position, and you can see that the 3D view here shows the movement of the mount. Note that until the mount is homed, the absolute orientation here is not accurate, as indicated by this message down here. Sometimes you may see, for example, that the telescope is pointing at the ground, but in reality it's not. It just, the axes haven't been initialized through the homing process yet, so it doesn't know exactly where it's pointing until that's complete. Once homing is finished, you'll see the visual representation snap to its correct position, and from that point on you can use this, for example, to monitor what a remote system is doing. Once homing is complete, it will slew to the first position that was indicated by the list of scans to be done on the previous screen, and then it will begin the frequency sweep process. As I described earlier, what happens is you'll see the mount oscillate back and forth, fairly slowly at first, maybe 2 times per second back and forth, and then it'll oscillate a little bit faster. And once the scan frequency gets up above about 60 to 80 hertz, you'll begin to hear the mount make some noises. Again, this is perfectly normal, and it's part of the process of characterizing the mechanical system that we're trying to control with these direct drive motors. Here we are about a minute later into the process, and you can see that we're now up scanning the 100 hertz region, and I can just barely start to hear the mount making some noises. As the frequency gets higher, you'll hear the pitch get higher. It works in generally an upward direction, but sometimes it bounces around if it needs to fill in more details at different frequencies. Once the first scan is complete, we slew to the next position. In this case, it happens to be the same position, but the second time around, we're going to be oscillating the azimuth axis instead of the altitude axis. Once again, we begin down at 2 hertz. You'll be able to visibly see the azimuth axis moving back and forth. And once it's established its baseline frequency, it'll begin moving up to higher and higher frequencies. Now here we are a few minutes later. We can see we're up in the several hundred hertz range. Okay, and once it finishes collecting all of the data, it comes to the next screen automatically, and we'll begin analyzing that data to come up with an optimal set of tuning parameters for your mount. And once it's finished, you can click the button to send the tuning parameters to your mount. After it's done, you can click here and disconnect from the mount. And then to test the system, we can go back to PWI4, connect, enable the motors, and make sure that we don't hear any sounds. We can try homing the mount and make sure that it moves smoothly, again without making any significant sounds. And we can try slewing to a point. I'll just click over here and choose Go To, and then watch the tracking graph. We should see that it zeroes in on its position fairly quickly. And the random tracking errors should be pretty low, like what you see here. If you were to push on either axis of the mount and let go, you should see it snap back into position fairly quickly. And that is the process for tuning the motors on your L-Series mount.